My dear students, let me welcome you all to a new edition of physics. And this edition will revise the first 3 chapters of the curriculum. You will be encountered with miscellaneous questions. Questions such as what happens when, write the scientific term, write the relation, give reason, choose. Also will be able to solve some problems. So let's get started. On the first 3 chapters. First question, mention an application of each of the following. So we want an application. Application on mutual induction, a device which is based on mutual induction. Okay. Of course, it is the transformer. Also, induction coil. Ruhmkorff coil is based on mutual induction. Application on self-induction. What is the device which is based on self-induction? Yes, fluorescent lamps are based on self-induction. A device which is based on eddy currents. Of course, they are induction furnaces. Induction furnaces. We want a device or an application of electromagnetic induction. Yes, sure, it is the dynamo. It is the dynamo. A device or application of magnetic torque, magnetic effect of the electric current. Okay, we've got many devices. It is the motor. Motor is one of them, moving coil galvanometer, also DC ammeter, DC voltmeter, and ohmmeter. They are all based on magnetic torque. Another type of question, what is the significance of the negative sign in the following expression? Okay, so we've got a relation, an expression, but we've got a negative sign. We want you to mention the significance of the sign. Once again, what is the significance of the negative sign in the following expression? EMF equals negative sign n is the number of turns, delta phi magnetic over delta t. What about this negative sign? What does it refer to? Okay, thank you very much. The negative sign in the expression indicates Lenz's rule. What about Lenz's rule? It states that Lenz's rule states that the induced current flows in such a direction. Induced current flows in such a direction to oppose the motion or to oppose the change producing the current, producing the induced current. Okay. Another type of questions. Write the mathematical relation that expresses. We want you to jot down the relation that expresses Ampere's circuit law. Ampere's circuit law. Okay, it is the relation that gives magnetic flux density, magnetic induction at a point of normal distance d from current carrying straight wire. So B equals mu I over 2 pi d, Ampere's circuit law. And what about the relation that expresses the law of conservation of energy? The algebraic sum of all voltages, second law of course of Kirchhoff's law, algebraic sum of all voltages encountered in any loop equals 0. So the relation summation of voltage equals 0. And what about the relation that gives the law of conservation of a charge? Conservation of a charge. First law of Kirchhoff. The sum of the currents arriving at any node, arriving at any junction in a circuit must equal the sum of the currents leaving that point. In other words, summation of current equals 0. Or the algebraic sum of the currents flowing into and out of a junction is 0. As I said, sum of currents equals 0. And what about the relation that expresses Ohm's closed circuit, Ohm's law of closed circuit? Okay. Of course, current through the battery, the main current, equals V battery over R capital plus R small. R capital plus R small means total resistance of the circuit, external resistances as well as the internal resistance of the battery. And now we've got a problem. We've got two wires as shown in front of you, okay, and a circular loop. So the figure shows two long straight wires, and of course they are carrying currents. So the figure shows two long straight wires that carry currents of the same intensity, that carry the same current intensity denoted by I1, but in opposite directions, and a loop that carries a current, I2. Okay, so the two wires carry equal currents, and this current is denoted by I1. And we've got a circular loop, and the current in the loop is denoted by I2. And they are placed in such that they've got just one plane, as shown in front of you. When a compass is placed at the center of the circular loop, it shows no deflection. And we want you to compare between I1 and I2. What does it mean a compass shows no deflection? It means the total field, total magnetic flux lines at this particular point is 0. Okay, so the fields cancel out. So once again, at the center, the two fields of the wire, okay, because they are equal. They are equal, so the two fields of the wire, 2B wire, is equal and opposite to the field of the coil or loop. So we can say 2 field of the wire or magnetic flux density is denoted by mu I1 over 2 pi R. Okay, your attention please. As a matter of fact, it should be I1 over 2 pi D, but the distance at the center of the loop, the point is located at a distance which is equal to the radius. So we can replace D with R. Okay, thank you very much. And magnetic flux of the loop is given by mu, number of turns on the loop, which is 1. Okay, current carrying in the, or current that flows in the loop is I2 over 2R. Of course, permeability will be crossed out. Also, 2 will be crossed out. And don't ever forget, number of turns is equal to 1. Okay, and radius is crossed out also. So we can say 2I1 over pi is equal to I2. And this means the ratio between I1 and I2 is pi over 2. So we managed to find the ratio between I1 and I2. We managed to compare the current I1 to I2. Another problem, okay, in front of you we've got a circuit. Okay, the circuit contains 13-volt battery of internal resistance. The internal resistance of the battery is 0, okay? And we've got a group of resistors connected in a certain way. We want you to use Kirchhoff's laws to calculate the value of the current in each resistance. So we want the current intensity through each resistor and the equivalent resistance of the circuit. Okay. Now let the current, the main current through the battery, let it be denoted by X plus Y. And a portion which is S will flow through the 1 ohm resistor. It is shown in front of you. Rest of it, which is Y, flows through the other 1 ohm resistor. At point B, actually a portion of the current denoted by Z passes through the 1 ohm resistor. So the current that flows through the 2 ohm resistor must be X minus D. And what happens at node D? Yes, Z and Y, yes, are added together to give Z plus Y that passes through the 1 ohm resistor. Okay. By applying, yes, Kirchhoff voltage law, KVL, on loop ABDA. ABDA. Okay. So minus X comes from the product of 1 and X. Okay. So minus X minus Z and plus Y must be equal to 0. So we can say Z plus Y is equal to Y. This is the first equation. Applying KVL, Kirchhoff voltage law, on loop ABCEFA. ABCEFA. Okay. So we can say minus X minus 2 between two brackets X minus Z plus 13, yes, equals 0. We'll rearrange this. So 2Z minus 3X plus 13 equals 0. And this is the second equation. By applying Kirchhoff voltage law on loop BCDB, loop BCDB. So minus between two brackets X minus Z plus Z plus Y plus Z is equal to 0. So X is equal to 2Z plus 0.5 Y. This is the third equation. Okay, substituting for X and Y in equation 1, Z is equal to 1 ampere, Y equals 6 amperes, and X equals 5 amperes. So X plus Y is equal to 11 ampere. R equivalent, of course, equals 13 over 11. Okay, it is VB over total current. So it is 1.1818 ampere. Another problem, a rectangular coil of 100 turns. So number of turns on the coil is 100. The coil has a length of 20 centimeter and width of 10 centimeter. The coil is rotated about an axis parallel to the length of the coil. The coil rotates or is rotated at a speed of 3000 rev per minute in a uniform magnetic field of density 0.28 Weber per meter squared. Okay, calculate the maximum EMF induced. Okay, EMF maximum, yes, is given by the expression NB A omega. omega equals 2 pi f. So EMF maximum equals 100 number of turns, magnetic flux 0.28, length and width should be in meter, so 0.2 times 0.1 times 2 times pi, 22/7. Frequency is given in minutes, so it is converted into seconds divided by 60. So maximum EMF equals 176 volt. Okay. Another item of the problem, describe the position of the coil with respect to the field lines after 5 milliseconds from the vertical position. Okay, a time of 5 milliseconds elapsed from passing the vertical position. We want you to describe the new position of the coil. EMF instantaneous is given by EMF maximum sine theta, because we started from the vertical position. Okay, maximum EMF, we managed to obtain it, 176 sine. Okay, 2 pi ft. 2 times pi here is equal to 180. F frequency, yes, 50. And time given 5 milliseconds. So 5 times 10 to the power of negative 3. Okay, so the instantaneous is equal to 176 sine 90. Sine 90 equals 1, so it is maximum. Okay, so it is the maximum EMF. Maximum EMF happens, yes, in the instant when the coil is in the horizontal position, where the plane of the coil is parallel to the field. Okay, so the flux lines are parallel to the plane of the coil. The coil is in the horizontal position. Another item of the problem, calculate the EMF induced when the coil rotates through an angle 60 from its last position. So the coil rotates an angle 60 from horizontal position. Starting from horizontal position, we have to use cosine 60, or if you want to use sine, it will be, yes, sine 90 plus 60 or sine 150. Okay, so instantaneous EMF is equal to maximum, which is 176 sine 90 plus 60, it will be 88 volt. And you could have used cosine. Okay, in this case it will be 176 cosine 60, and of course it is 88 volt. Another item of the problem, we want you to calculate the effective value of the EMF induced. It's all easy. Effective value, EMF effective equals EMF maximum times 0.707. So it is equal to 176 times 0.707. It is 124.4 volt. Another item, we want you to calculate the average EMF induced in the, or average EMF induced as the coil rotates through a quarter of a cycle, quarter revolution. EMF average equals NAB or NBA times 4F. F is the frequency. So average EMF equals 100 times 0.28 times 0.2, 0.1. These are the dimensions of the coil. Okay, times 4, and frequency is given 50. 3000 over 60, it is 50. It will be 112 volt. And of course, you remember the negative sign refers to Lenz's rule. Another item of the same problem, when the coil is connected to a standard, or if the coil is connected to a standard resistance of 200 ohm, find the power consumed, yes, through or in this resistance. neglect the resistance of the coil. Power is given from the formula I effective, V effective. Okay, so it will be 77.37 watt. In front of you, we've got a diagram. It shows the variation of the EMF induced versus time. Okay, so the figure shows the variations of the electromotive force generated by a dynamo coil that revolves at an angular velocity omega. Okay, in the figure, maximum EMF is equal to 100. Periodic time is 20. Periodic time of one cycle is 20 milliseconds. And now, what about the question? Find the frequency of the rotation. Frequency of rotation, it's all easy. Frequency is the reciprocal of the periodic time, 1 over t. So it is 1 over 20 times 10 power negative 3, 1000 over 20, it is 50 hertz. And now draw a graph, sketch a graph to represent the change in the EMF generated in the dynamo in 20 milliseconds when it revolves at an angular velocity 2 omega. So angular velocity is doubled. Okay, we want you to redraw it once again, but after doubling the angular velocity. Okay, in front of you, the two diagrams are shown. The first of all, maximum EMF will be doubled. Instead of 100, it will be 200, and number of revolutions, yes, is doubled. For example, in a time of 10 milliseconds, we've got half cycle in the first part, but in a time of 10 milliseconds, we've got a complete cycle. Okay, in 20 milliseconds, we've got just one cycle, but in the second diagram, we've got two cycles. Okay. Another type of questions: when does each of the following quantities equal 0? When does each of the following quantities equal 0? The torque acting on a coil carrying an electric current and placed in a uniform magnetic field. Okay, torque equals 0 in the vertical position, where the plane of the coil is perpendicular to the magnetic field. Vertical position means field lines are perpendicular to the plane. Torque is given by the expression BIA and cosine theta. Theta is equal to 90. Okay, cosine 90 equals 0, that's why the torque is 0. When does the magnetic flux at any point inside and along the axis of a current carrying solenoid equal 0? This happens when the coil, the solenoid, is made of a doubly wound wire. When the solenoid is made of a doubly wound wire. When does the EMF induced in a wire moving in a uniform magnetic field equal 0? A wire moving in a magnetic field, but no current is induced, no EMF is induced. The wire must be moved parallel to the field. When the wire is moved parallel to the field, EMF induced equals BLV sine theta. So it will be equal to 0 when theta is 0 as sine 0 equals 0. Okay, and don't never forget, theta is the angle between field lines and direction of motion of the wire. When does the force of a magnetic field on a current carrying wire equal 0? Okay, when the wire is placed parallel to the field. The wire is placed parallel to the field, then no magnetic force will act on it. Okay, force is given by the relation BIL sine theta. the force equals 0 when theta equals 0. When does the difference between MF of a cell and its terminal voltage equal 0? So it asks when actually MF of a cell is equal to its terminal voltage. As a matter of fact, it happens in two cases. When the circuit of the cell is open, that is to say, resistance across the terminals of the cell is infinite. Okay, no current passes through the cell, then V battery equals terminal voltage. Okay. Also, it happens when the internal resistance of the cell is 0. And this way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.